Hey there. So we're going to take a look at the very last example for section 6.3, which is also the very last example in the course. So we have, for this example, we have one of our old pals from section 4.2. And if you remember in 4.2, in chapter 4, we were just learning how to handle having a second order differential equation that was non-homogeneous, which is really a fancy way of saying having a harmonic oscillator that has a forcing function. Now, it doesn't have to be a harmonic oscillator with a forcing function, but that's kind of our metaphor for understanding it. We have a second order differential equation that has a y or y prime or y double prime term. This is just a function of t. We also have some initial conditions. So just from a perspective of, we've seen this before, we actually know what the solution is for this. We've seen it once before. But now what we're going to do is use the Laplace transform method. So let's try using the Laplace transform method on this. If you remember using the kind of lucky guess method, we had to come up with a guess for this side. We had to solve the homogeneous portion and then come up with a guess for this side. And it was kind of multi-part. But what we can do with the Laplace transform method is just apply the Laplace transform all the way across. We've got Laplace transform of y double prime plus 6 times the Laplace transform of y prime plus 8 times the Laplace transform of y. The other side is going to be negative 4 times the Laplace transform of cosine 3t. And we've got our initial conditions that are going to come in handy here in a second. And so you probably can notice right away that if our initial conditions are both 0, this side of things is going to simplify kind of what we noticed in that last problem. If our initial conditions are both 0, we're going to be kind of sneaky and say, oh, then this is just going to turn into s squared, excuse me, times the Laplace transform of y plus 6s times the Laplace transform of y plus 8 times the Laplace transform of y equals negative 4 Laplace transform of cosine 3t. We'll deal with him in a second. Now, in order to go from here to here, technically you could rewrite each one of these and say, okay, that's s times the Laplace transform of the differential, or excuse me, the y prime, the Laplace transform of y prime, and then have to do it one more time. But you wind up with s squared, and there's no extra term from our initial conditions. And I'm going to kind of underline this and say, since the ICs are both 0, we can kind of make that leap. If they weren't equal to 0, then sorry, no can do. But for us, that means we've got a polynomial, s squared plus 6s plus 8 times the Laplace transform of y on this side. The other side is still equal to this guy. But we should be able to figure out what the Laplace transform of that is. And because we've got the negative 4, he's going to be along for the ride. The Laplace transform of cosine 3t we can get from our table, or we can hop on Maple and do it if we want. Cosine 3t is going to be s over s squared plus 3 squared. So this is going to be negative 4 times s over s squared plus 3 squared. Or you can write 9 if you wanted to. And so the last step is just to solve this thing for Laplace transform of y. And we now have negative 4s over one polynomial, s squared plus 9, times another polynomial from over here, s squared plus 6s plus 8. Now, you might be looking at that and thinking, oh, I don't think I could undo that using the Laplace transform, but thanks to our ability to use partial fractions in Maple, we can do this. So I'm just going to write a little note and say use parfrac in Maple. Or if you want to do it by hand, you're more than welcome to do it by hand. I would not recommend it just because it's boring and we're not in Calc 2. So using partial fractions, you find out that you have Laplace transform of y equals, on this other side, you can pause for a second and practice doing this in Maple. But you'll wind up with, actually, it turns into 1, 2, 3, 4 fractions because we have 2 quadratics down in the bottom. And so the first one is 4 over 13 times s plus 2. The next one is plus 4s over 325 times s squared plus 9. And then we have minus 216 over 325 times s squared plus 9. And then minus 8 over 25 times s plus 4. Now, if you're paying attention, you'll notice that each one of these is remarkably unique, or not unique, remarkably similar in the sense that they have a constant, in this case 4 over 13, in this case it's 4 over 325, negative 216 over 325, negative 8 over 25. And so we could factor each one of those out and treat them, in this case, we have basically 1 over s plus 2, that's an exponential. When we do a Laplace inverse, 1 over s squared plus 9, that's going to be a cosine. 1 over s squared plus 9, that's another cosine. Or excuse me, in this case, I think it's a sine. What did I do different? I'm not sure. I have to take a look at that one here. Hold on. I have to pull up the Maple. Maybe I should pull up the Maple so we can make sure that I wrote down the right thing here. Hold on, let me pull up Maple. Okay, here we are in Maple, just to make sure I did it right. So I typed it in, times 1 over that guy. Oh, I see what the problem was. So this first one is 4s over this junk, and the other one is just a constant. Ah, that's why. So let me switch back here. So this guy right here, there's an s over s squared plus 9. That's what makes it a cosine. And this guy right here becomes a sine. So, duh. So now what I can do is use my inverse Laplace, and I'll be left with just my y of t. So let me make a little note and say, yeah, we're going to do inverse Laplace. And when I do that, I'm left with y of t equals 4/13, and 1 over s plus 2, that's e to the minus 2t. And then this guy is going to be plus 4 over 325 times s over s plus 9, that's the inverse Laplace of that, is going to be our cosine 3t. The 3 is coming from the 9. And then 216 over 325, that's going to be minus, this simplifies a little bit, I think. 72 over 325 is going to turn into, does it? Does it simplify? No, I guess not. 72 over 325. Is it 72 over 3? Yeah, divide that by 3. Yeah, 72 over 3, not over 325. What am I doing? Over, hold on, I got to think about this. I think I see the problem. It's because there's a 3. There's going to be a 3 on top. Yeah, so this will be 72 over 325 times sine of 3t. And then our last term here is going to be 8 over 25, so minus 8 over 25 times, this just becomes, when I inverse Laplace, e to the minus 4t. And again, don't take my word for it. You can go piece by piece, and you should be able to decode each one of those terms using the tables, because each one of these is totally a table situation. So the one kind of note that I had forgotten to make to myself here is that 216 is the same thing as 72 times 3. And so that 3 I needed sitting up top here. And so that's 72 times 3 over, and then that's where the 3 cancels with the sine of the 3t. That's where it comes from. So after a little bit of effort, you can find out that a little bit of maneuvering this thing around, I'm going to rewrite this in a slightly different form. I'm going to write it as 4/13 e to the minus 2t, and I'm going to pull this term over here, minus 8 over 25 e to the minus 4t. And then I'm going to put my two periodic terms together, plus 4 over 325 cosine 3t minus 72 over 325 sine of 3t. And if you look carefully at this, and if you flip back in your notes to section 4.2, you'll find out that this is exactly what we got last time, and it's made up of two parts. This is what we called the natural response. Right? That's our harmonic oscillator if there were no forcing function. This is how it would behave. Exponential decay in two different forms there, but it's exponential decay. And then this, of course, in the long run, that's going to define how our harmonic oscillator behaves. This is the steady state response. So if we wanted to, if we were asked, how is this harmonic oscillator going to behave in the long run? That's how it's going to behave in the long run, because as t approaches infinity, these two terms just kind of disappear. They become zero. So if you take a look at this thing, you find out that it's mostly just a little bit of algebraic manipulation with some help with parfrac from in Maple. But this is really a straightforward solution process for what was in Chapter 4 a fairly complicated forced harmonic oscillator problem. Right? So the Laplace transform method works for us. It allows us to solve our harmonic oscillator differential equations in a fairly straightforward fashion. The key, though, is we have to have those initial conditions, and it's really nice if the initial conditions are both zero. It makes it so much easier to jump ahead. But that gets us to the end of 6.3, and it gets us to the end of the course. So hopefully you can take that for a spin. You'll notice that there's an extra page after this, but we don't really need it. That was just extra in case we wanted to do a little bit more algebraic work, but I'm not all that interested in doing the algebra. It's more fun to talk about this and try to explain what's going on. So in Maple, I went ahead and did the inverse Laplace of all that junk, and I came up with the solution that we had from the start. And I think up here I had also, did I solve it? Yeah, I solved it using just a D-solve. And you'll notice that the D-solve for my forced harmonic oscillator with damping, with initial conditions, gives me exactly the same solution. So we can solve this particular problem 3 different ways. Well, actually, if you want to think of it, 4 different ways. We can solve it, kind of let Maple do its thing and do a D-solve. We could do a numerical solution in Maple, which, why bother? We can do a lucky guess for the particular solution, kind of solve the homogeneous side, and then solve for the non-homogeneous whole thing with a particular solution, that kind of what we call the lucky guess method. And you can do that either with a complex lucky guess, kind of complexified lucky guess, or you can just use a cosine plus a sine if as a lucky guess. And last but not least, of course, we can do the Laplace transform method. So there's like 4, maybe even 5 different ways that we can solve these problems. And that gets us to the end of the course. So we've learned a whole bunch of different ways to solve these problems. Hopefully you get a chance to practice a little bit, and I will see you next time.